Welcome everybody to today's Protocol Labs Research Seminar. Today we have Jan Michalevsky and Yonatan Winetraub from Cryptosat. Jan received his PhD in Applied Security and Cryptography from Stanford University, where he was advised by Professor Dan Benet, while Yonatan earned his PhD in Biophysics at Stanford University School of Medicine. Both are co-founders of Cryptosat, a company whose mission is building satellites that power cryptographic and blockchain applications. Today, Jan and Yonatan are joining us to present their work titled Cryptosat, Secure Computing in Space Using CubeSats. From that, I'll let you both take it from here. Thank you so much for joining us today.
Thanks, Trent, for the introduction. So maybe first we'll quickly talk about kind of the context for this research and generally how it can respond. I'd love to actually start maybe with Yonatan presenting himself and giving a quick background about his aerospace background. To explain kind of where this collaboration came from.
Basically, Jan is a crypto guy and I'm the space guy. My background is aerospace engineering. I built satellites. My latest was the first private moon mission. I was co-founder of SpaceIL, which crash landed on the moon in 2019. We always say that every startup wants to make an impact. Well, we certainly did one. And I bring the space side of the Cryptosat.
Yeah, essentially, myself, as Trent already mentioned, I bring the cryptography background. So essentially, the way this idea started is that at the time, I was kind of nearing the end of my PhD studies and was looking into what's called trusted execution environments of different sorts and also hardware security models. So trusted execution environments, as we'll explain in this talk, is basically kind of tamper-proof, ideally tamper-proof environments that can guarantee integrity and potentially confidentiality for computations. Some of those are integrated into just regular CPUs nowadays. So if anybody heard about things like Intel SGX, secure enclaves, ARM Trust Zone, those are some examples of trusted execution environments. And in fact, pretty much in every kind of iPhone, you have what's called a secure element that can say check, validate your fingerprint, and then instead of providing it to the cloud, it kind of keep this data private, the fingerprint itself private, and then only signs some statement that tells that it checks. It checked and validated this fingerprint and it matches. So then the cloud can authorize the user to access some stuff and without kind of getting the private biometrics. So those are just some examples. I was kind of looking into those kind of things. And then essentially there was this idea of kind of combining it with space tech and kind of thinking, wouldn't it be cool to essentially protect those computations in space by putting them in a satellite? I didn't know anything about it, and Yonatan knew everything about it. So basically, we wrote a paper back then, and that resulted in a submission to a workshop at the time that was called ASHES, Advances in Hardware Security, to a track that was called Wild and Crazy. So if you kind of look up SpaceTEE, you'll find two versions, one the archive version, and then you'll also find the workshop submission, which is titled WAC. WAC stands for Wild and Crazy, that went to this track. Yeah, and it actually resulted after some time. So at that point, we left it kind of on the shelf. We put this idea aside. We were happy with getting it into this workshop. But about a year ago, a friend approached us, Gil Shaitan approached us and in fact convinced us that we should actually productize this thing. And we started working on what today is Cryptosat. So, okay, so I kind of talked enough about the history of that. So I'll get to actually explain what this is about. And I'll talk about kind of the crypto protocol ideas we designed on top of that, and Yonatan can answer throughout the talk anything that's related to the space aspect. So feel free to chime in and ask any questions. I think we have enough time. It's not like a short conference talk, we have enough time to kind of for you guys to interrupt and chime in with the questions. All right, so this talk essentially doesn't reflect some of the newer ideas. Sorry, I'll just pause my Slack notifications are bugging me, so I'll pause all of that. So this talk actually doesn't contain some of the newer ideas around applications to the blockchain space. It's based on the workshop talk I gave at the time at the Ashes workshop, and mostly talks the Web 2 application, but also touches on some blockchain aspects, and mostly focuses on kind of how to design a protocol on top of this trusted execution environment. So this was called, we called it at the time SpaceTEE, which stands for a Space Trusted Execution Environment. And it's a platform for secure and tamper-proof computing in space using CubeSats, Cube satellites. So first, I want to motivate why we need these or trusted execution environments at all. We need them for confidentiality because we sometimes need to make sure that the inner state is invisible, essentially the inner state of the computation. There are all kind of examples of that. First of all, the data itself you might be operating on might be sensitive. Second, specifically for cryptographic operations, I guess, yeah, there was a question in the chat. Everybody sees the slide titled "We need TEs," or sometimes when the platform is performing cryptographic operations specifically, you want the inner state of the kind of operations that involve the keys to be invisible, because otherwise the keys can be extracted. So you need this for confidentiality. And also you need TEs for computational integrity. Sometimes you're offloading some computation to a platform that you don't necessarily trust, and you want some trusted execution environment to be part of it. That guarantees that the computation over some inputs was done correctly. Essentially that the platform executed exactly the code and the algorithm that you would expect it to execute and didn't tamper with the results that it produces. And that enables you, for instance, to offload certain things to some untrusted infrastructure if it has this trusted execution environment that you can verify. So that can be used as some trusted authority or attesting to certain things, and there's a verifiable computation. Verifiable computation essentially is not always practical. So we're familiar with the cryptographic constructions for that. They're essentially proofs of running some computations correctly, but they have all kind of downsides, including kind of the sizes of the proofs, the time it takes to verify them. Sometimes it's very large public parameters that are required to support those proof systems, and they're not trivial. So sometimes the kind of the simpler conceptually approach is basically to just have a platform that you assume you can trust and does things correctly. And some of the kind of applications on top of that can be around key management, authentication, digital rights management, and things like, say, preventing cheating in online games. Another example is trustworthy grid computing, essentially to prevent, for instance, laziness. So say you're floating a lot of computation to the cloud, to some infrastructure that you don't control, and you're getting some results back. There might be an economic incentive to actually not perform those heavy computations and just give you some bogus result that's some random thing that the cloud sends back to you without actually spending the computational resources to produce this to run this algorithm correctly. The problem with trusted execution environments, though, is that they can be potentially attacked if you have some physical access or sometimes less direct access. And there were several examples or multiple examples of side channel attacks on those trusted execution environments. So even though they can be sort of architecturally implemented in a reasonable way or securely implemented from the standpoint of the architecture itself, there might be all kind of surprising ways to get around the architecture itself. So some examples were seen around attacking hardware security models or just attacking computers directly, or even platforms that such as Intel software guard extensions with different side channel attacks. So for instance, Gamkin and his co-authors demonstrated interesting things like key extraction from electromagnetic radiations, or key extractions from acoustic cryptanalysis. Essentially, they were able to kind of put microphones not far, in some distance from a laptop, and while they're performing cryptographic operations on this laptop, encrypting something, they were essentially able to monitor the acoustic emanations. They essentially kind of looked at what the microphone, the signal that the microphone is capturing, and by looking at the signal, they were able to infer and kind of deduce different bits of this secret key, and sometimes even partial extraction of the key results in a complete break of a cryptographic system. And they did something similar also with electromagnetic emanations with a small antenna. So that was a funny presentation that actually showed how this circuit, including the antenna and some boards that capture the signal, can be fit into a pita bread. So a pretty small device that can be pretty stealthy and can help you break and kind of sidestep the cryptographic protections of some computer nearby. Related to this, there's also this whole domain of hardware security models. It's a pretty big interesting industry. It's essentially more than $1 billion market, growing. And those are essentially appliances, hardware appliances that on one hand can just kind of do cryptographic operations, and on the other hand, they contain different protections to protect those models from physical access, tampering. And so essentially, those are kind of boxes that you can connect to through APIs. One of the standards around that is PKCS11. And you can ask it to store keys or sign cryptographically some messages for you, and so on and so forth. And some of them, kind of the high-end HSMs, they have sensors that can detect if somebody's getting close to the HSM, tries to open the enclosure, tamper with the appliance. And there are different levels. There's actually a standard for it called the FIPS 142, and there are different levels. So there can be a level 2 HSM, which is kind of on the lower end of those appliances. Level 3 is pretty high-end, and then level 4 is the highest level, and those devices can be really expensive. So we found that those devices can cost around $100K. It's used often in regulated industries. So, for instance, in banking, that have a really stringent requirements around protecting keys and cryptography, and that's why it basically results in this big industry around that. Whatever protections you apply, given physical access, there are still concerns, and there have been demonstrations of getting around those protections of HSMs. And there's also the kind of the issue of the cost around the really high-end ones. So whatever you do around that, you basically run the risk of somebody being able to break it. So what on earth can we do? And the answer is that maybe we can do something that's not on Earth. So the idea is that objects in the outer space are very hard to access physically, but they can communicate with one another, and they can communicate with terrestrial base stations. Around the nine service and the nine access to things in space. So there are anti-satellite weapons that are able to destroy satellites, but capturing is extremely difficult and expensive. It's not something that really has been demonstrated, and it will likely be evident. So Yonatan, maybe you want to chime in and elaborate a bit on the NORAD system for monitoring.
Yeah, so the main security assumption is basically there are networks of radars that are scanning through the sky, and they're able to detect any metallic object that is larger than a couple of centimeters or a couple of inches. So if you are having an asset in the sky, this network of radars is going to detect that, and multiple nationalities have different networks. So it's actually very, very difficult to launch into something into space without having any radar detecting it. And since orbital mechanics is a slow process, rendezvousing with a satellite is actually a long process. So you're going to have a long warning of when a metallic object is getting close to you, anywhere close to you before you do that. So it's really difficult to stealth, sneak up to satellite, and because it's open space, the signal to noise ratio is really in the favor of the satellite trying to defend itself. There were some demonstrations of destroying this satellites. It was the latest one just a couple of weeks ago. But again, this is a denial of service attack. This is not something that you can actually capture a satellite and hack into it. And there's a huge asymmetry in cost. Launching a satellite is very easy. Getting to rendezvous with another satellite or destroying it's actually very expensive.
It's important. What I want to second is that essentially destroying those satellites can only impact availability of such a service and doesn't impact security. We can essentially keep launching those, and this whole idea is predicated on this asymmetry that Yonatan mentioned, that it's pretty affordable to launch those satellites that will serve the cryptographic applications, and would be very expensive to destroy or jam the transmissions and prevent them from providing service. Similar to NORAD, there are essentially a couple of different independent agencies that are doing those monitorings of countries belonging to countries that are not colluding. So one run by the NORAD is run by the US, right? There's another one run by Russia and China. So essentially countries that are not the closest friends, and kind of this independent monitoring can guarantee that nobody is really providing an untruthful view of what's going on there. So with this, the idea is essentially that space can serve as our trusted execution environment to protect those sensitive operations. So the idea is, in terms of implementation, in terms of what kind of satellites we want to use for that, essentially the idea is to use what's called CubeSats, Cube satellites. It's and specifically this CubeSat 1U is this small box, this kind of enclosure you see on the top right, and next to it you see this coin, just to kind of give you the proportions. So it's essentially 10 by 10 by 10 centimeters. It's a very small thing, but it's a fully functioning satellite, and it weighs a little more than a kilo. Depends what you put inside of it. So it's a pretty small satellite, and it makes it very affordable to launch it. The cost of launching it is not in the sky. At the time of writing this paper, it's been reported that there were 699 CubeSats launched. That was as of June 24th, 2017. Now it's probably way more. Essentially, the overall cost of the solution we estimated, including launch, back when we were writing the paper, that was less than 100K. So that's already comparable to commercial level 4 HSMs. So in terms of the cost of launching such a solution, that's not necessarily way more expensive than essentially onboarding this box where you still need to worry about physical access, and people are not really happy kind of with the not exactly happy with what HSMs provide today, and also the security still remains questionable with the terrestrial HSMs. So there are those security advantages the system can provide at a comparable cost, if not less. Based on our more recent estimates, since we started working in Cryptosat, those costs can even go down further if you don't just kind of buy hardware provided by vendors, but potentially buy the components on your own and assemble your own satellite from scratch. So it's possible to bring those costs to a way lower figure. This slide talks about some of the pre-launch protections. Essentially, in this whole model, we have this kind of punctured trust model. Essentially, there's zero trust from the moment the satellite is launched into orbit, because then it's physically inaccessible. You cannot, if you kind of don't provide any upgrade APIs, you cannot change the code. So you can completely trust this platform. But there are questions around kind of what happens before the launch. One specific point is between the assembly of the satellite, between the building your satellite, and between the launch itself. So for instance, if you trust the assembling party, or there's a ceremony around that where the assembly of the satellite is validated and observed by kind of independent parties that make sure that the hardware is the correct hardware, there are no malicious components put in. There's still kind of the storage of the satellite between the assembly and the launch itself. And it might be important to make it tamper evident. So one idea that was discussed in our paper, and that's a very cool idea that Yonatan came up with, is essentially using this covering that would make it evident if somebody tampered, if somebody tried to open it and introduce new hardware or tamper with the hardware in between the moment you assemble the satellite and the launch itself. So there's something called captain tape, and you can basically, once you have this nice satellite assembled, you wrap it with this captain tape, so it won't look as neat anymore. It will be wrapped by a bunch of tape, and then you measure the moment of inertia of this thing, basically the physical moment of inertia. So you can measure it on Earth, and then it's possible basically by tracking antenna spin via Doppler effect to observe the moment of inertia, measure the moment of inertia once the satellite is in orbit. And any change, if somebody tries to kind of unwrap this captain tape, introduce some new hardware, and then wrap it again to reintroduce the same moment of inertia, that's something that's hard to do. It's hard to kind of get it to the same state. So essentially what the idea is to kind of measure it before, right after assembly, and right after wrapping with this captain tape, and then keep monitoring the moment of inertia once the satellite is in orbit, and compare the two figures and make sure that they're close to one another within some threshold. Yonatan, is there anything to add to that, or clarify anything around this technique?
Yeah, so one thing that is key here is that actually the technology of replicating moment of inertia in 3-axis is, and for any practical reasons, not existent today. Like, you can emulate 2 moment of inertias, you cannot have the 3-axis. So as long as you wrap the captain in a random way, that is not completely evident when you unravel it, what you did there, this makes it very, very difficult to impossible to imitate, even if you had very sophisticated equipment.
That's a pretty sophisticated protection. For instance, in practice, we still need to understand kind of what kind of trust users will have in this in such a system. Is this protection actually needed in practice? And one thing that Cryptosat is going to do down the road is better test this method and do some more research around how easy it is to implement it. What's the threshold between what's basically the threshold of the difference between the measured and the observed moment of inertia, and basically test this technique further to kind of make it ensure that it's indeed practical. But that's the rough idea around this. So essentially, on top of this, that's kind of so far I presented the general idea of doing some computations in the satellite, and now we're going to talk a bit about the applications of that and what protocols we can build on top of that, based on that, also taking into account the constraints of the satellite and the communication with it. So essentially, the paper discusses something called the SpaceHSM, an HSM designed on top of this trusted execution environment in space. And using that as a building block, describes a system that can serve as a certificate authority, and also serve towards what's called certificate transparency. So I don't know if everyone is familiar with certificate transparency. in the kind of normal internet. Certificate transparency logs is something that prevents powerful attackers who can get access to. Before I describe the kind of the certificate transparency log that's specific to the satellite, I'll first describe what it means for the internet. So essentially, it's a system that prevents attackers that were able to take a hold of a CA, such as VeriSign, DigiNotar, Komodo, something like that, basically attack users by forging certificates, basically getting access to a CA and getting its some private signing key. They would be able to forge certificates, and one way to prevent that from being kind of persistent long-term attack is to use the certificate transparency log, which is something where users constantly transmit their certificates to, and the system is kind of a ledger of for all the certificates that were reported to it and that were issued by different CAs. You can actually think of it as kind of something similar to a blockchain. It's not exactly blockchain, but it's a ledger. It's a ledger that basically records what certificates have been issued, and there are monitoring parties. So there are independent monitoring parties. I probably don't remember all of them at this point, but there's one that's run by Google, one that's run by Mozilla, by Cloudflare. Essentially, there are multiple independent companies that monitor those certificate transparency logs. Some of them also kind of run those logs that collect those certificates. And there are all kinds of techniques around aggregating those, and instead of you kind of going through all the logs, which would be a terrible complexity, you can basically have accumulators for that, or proofs of memberships, or things like, think about something like a Merkle tree, where you can kind of check the root that certificate that the certificate transparency system provides to you, and kind of check if a certain certificate is part of this all this set of reported certificates. So essentially, on top of this SpaceHSM, we designed the certificate as something that can help this kind of system to prevent attackers from forging certificates. So on a high level, the idea is like that. You have ground stations that submit a certificate signing request to the SpaceHSM, which also updates an accumulator. Essentially, it has kind of a record of all the certificates it's seen, but it doesn't need to store them all. It essentially has like a short accumulator that summarizes sort of the sequence of all the certificates that were transmitted to it for signing. And then it can transmit this accumulator, and there are other ground stations that essentially provide this access to public certificate logs, and they retransmit this accumulator, and the accumulator is signed by the satellite. So essentially, the SpaceHSM here serves as the root of trust and a cryptographic accumulator. And the ground stations, they just delegate data. They essentially delegate the certificate signing request and also provide access to this public append-only certificate log. And then another party in this protocol is the verifier. That can be any user, essentially anybody who is presented with some certificate. Say somebody browses, goes to google.com, gets a certificate, and they want to check whether it's a legitimate certificate that was recorded or at least has been seen by this infrastructure. They essentially can check it against this accumulator and check it against proof of membership. And in terms of the specific accumulators, you can use different techniques for that. It can be something like just a Merkle tree of all the received certificate signing requests, or it can be some RSA accumulator. So there's some flexibility there in terms of picking the most suitable scheme for that. We also defined two different threat models. One of them was one of them was not taking into account denial of service, and the other one is taking denial of service and provides some more techniques to prevent that. So in terms of the assumptions, essentially we assume that the SpaceHSM is tamper-proof and that there's no physical access to it. And regarding the adversary, we assume pretty strong capabilities. So essentially, we assume that the adversary can physically access all terrestrial infrastructure and can potentially compromise it. And it can occasionally access the communication channel with the SpaceHSM and bypass the security of the ground station. And it also has full read access to code. So the code of the SpaceHSM is not secret, it's available, and to the data of the SpaceHSM prior to launch. And then we also assume that spoofing the SpaceHSM transmission is impossible. So maybe it's not exactly possible, but it's impossible in the sense you can transmit something, but you won't be able to sign those transmitted messages. So that's essentially how you prevent somebody from spoofing communication from the SpaceHSM. The protocol to implement this system is like that. Essentially, there's a bootstrap stage. That's one step. There's a certificate signing request, and there's a certificate log update. So in terms of the bootstrap, we have this first step where the satellite is launched into orbit, and then it generates a keeper and starts broadcasting it for a while. So essentially, it broadcasts the public key corresponding to this keeper. And multiple ground stations over this time can receive this public key, can gossip between them, compare it, and make sure all the terrestrial infrastructure and the users that want to use the system have the right public key. So that's something that would be hard to work around because essentially it's not one party that transmits this public key. You can essentially build your own amateur ground station, use some antenna to receive this public key, and kind of users can independently verify it if they're really paranoid, or at least you'll be able to have multiple ground stations tell you that that's the public key they received. So you make sure that everybody agrees on what the satellite has generated. In terms of the certificate signing request, essentially you send it a certificate request, and the SpaceHSM transmits back a signed certificate. So what it tells you is basically that the SpaceHSM saw your certificate. That's all, pretty simple. And what it does in terms of the state it stores, it essentially updates its accumulator, the cryptographic accumulator, and starts broadcasting the updated accumulator. So it continuously broadcasts the accumulator value, and whenever there's a certificate request, we expect to see a change in this value. In terms of the log update, every signed certificate is expected to be submitted to this certificate log, and the log server verifies the certificate and appends it to the log. Now we want to add to it the consideration around denial of service attacks. So this considers an adversary that attempts to prevent access to the system or kind of get it into a state that would make it non-operational. The motivation for that wouldn't be just kind of the short term. It's essentially creating some asymmetry in terms of the cost of operating such a system, because if you have this satellite that is powering the system, and you get the system out of order, it will be pretty expensive to. It will be affordable, but still there will be a cost to launching a new satellite or switching to using a different satellite. Essentially disrupting this system can be pretty costly. What the attacker can try to do is submit certificate signing requests to the SpaceHSM, or try to withhold signed certificates from the log. What we can do to counter that is have the SpaceHSM broadcast the signed certificates instead of just sending it to the ground station by the private channel. So then everybody can see that a certain certificate was included in the log. And there are additional measures we discuss in the paper around the rotating keys. If somebody transmitted something that kind of puts the system in a weird state, and then you have kind of ways to sort of back up the previous state and retract to it, which is something that's limited to some administrative users of the system. And is only possible if you have some keys that are not usually accessible. They are stored in cold storage. Those are essentially backup keys that enable you to sort of revert the system and the log to a previous state. So that enables you to kind of recover the certificate transparency system without the need to launch another satellite. And the idea is that the access to those keys is really kind of physically limited and is only accessible to some operators of this system. Now I want to talk a little bit about the CubeSat design itself, and that would also make it more clear in terms of what are the operational constraints and what are the computational constraints around this system. Essentially, this enclosure, this CubeSat, contains an onboard computer that runs the actual computations. It has a solar powering system, and it has antennas connected to it. And there are two types of antennas, VHF and UHF antennas. Yonatan, maybe you can elaborate on the implications of using one or the other.
VHF, UHF, for those who were living in an old building apartment, if you look at the roof of that apartment, you'll see a VHF, UHF. These are antennas that are used for TV transmissions for the most part, just because they travel very long distances. The antennas are very simple, and their wavelength is comparable to tens of centimeters to a meter, I think. So this is a very simple standard band to work with, known very well. The higher you go with the frequency, the shorter the wavelength becomes, and then more data you can transmit. So that's the key limitation of this kind of wavelength, is that you can't really transmit megabytes of data per second. This is in the order of low kilobytes per second. So that's a key limitation of those antennas. However, VHF, UHF is readily available and supported by amateur radios and amateur ground stations around the world. So this is a very good infrastructure if you want to start off the ground. However, most satellite operators, and us included, are thinking about going into higher bands in order to enable this higher data rate that is not feasible with VHF, which is very high frequency, and UHF, which is ultra high frequency. See, people were not very creative in the names, maybe.
And I think one interesting thing to note here is that you can use pretty standard hardware and processors in this system. So, for instance, we examined the different options back then. So one processor that's common in those CubeSat satellites is the ARM processor. So you can use an ARM Cortex M3, which is a pretty powerful ARM processor, at least for kind of the cryptography that's needed for this kind of a system. So that makes kind of things easy to program. And in terms of the power budget for that, essentially the solar panels and kind of the charge that you can accumulate whenever you whenever the satellite is lit, whenever it sees the sun, that essentially can be enough to operate the satellite throughout the whole revolution around the Earth. So it accumulates enough charge when it has sunlight, and then it can operate for a while. And kind of we model this in the paper and do all the calculations around the availability of the service. Another thing to add here is that this enclosure can actually accommodate two independent boards. So you can actually have two independent SpaceHSMs that can potentially serve to different cryptographic applications or to different certificate ledger systems in one enclosure. And essentially one power supply can power both. And it's enough to operate those. So you can essentially kind of have two systems in one physical satellite. So largely, essentially in this CubeSat satellite, we can use commercial and tested off-the-shelf parts. In terms of where it's launched, so it's launched into what's called the sun-synchronous orbit. It's a low Earth orbit. In terms of the Cube computer, we picked a 32-bit ARM Cortex-M3 with 4 megabytes of flash memory. So sounds like not much, but it's essentially enough to for the code and for storing this cryptographic accumulator that's needed to at least for this application. You can see that the clock rate here is 48 megahertz specifically for this setup, which is not too much, but that's not the bottleneck given the receive the transmit channel and the amount of data that you need to operate on. So this should be enough to power this application. As I mentioned, there's a calculation of the power budget. So there are 45 minutes of daylight and then 45 minutes where the satellite doesn't see the sun. So during the first 45 minutes, it's charged and then it operates on this charge. And there's a estimate of for the power consumption, which essentially amounts to enough to power 2 of those SpaceHSMs in one satellite. The other thing that's interesting to look at is the bandwidth and the delays in communicating with such a satellite. And here, an uplink, such as the transmission to the satellite, is pretty low. So that's 1200 bits per second. And in the paper, we do this computation of how many certificate signing requests can be supported by such a system. So an average certificate size is something like 2.5 kilobytes. And that enables to serve 1 certificate sign request every 20 seconds. So what it means is essentially that's not something that can immediately with this setup at least to replace the terrestrial certificate transparency system for the whole internet, right? Now there's such an immense use of certificate transparency that essentially gigabytes per day. So that wouldn't be possible with the system, but potentially it can be used for sort of the most sensitive certificates, not for just every certificate that's issued every day. There are ways to increase the communication bandwidth. So maybe Yonatan, you can elaborate on the different ways to do that.
The main driver here is the native frequency of the radio electromagnetic waves, and they can carry as much information as comparable with the frequency or proportional to the frequency. So going to higher frequencies, which means lower wavelength, is the way to go. The obvious next option is what's called S-band. This is the kind of where the Wi-Fi frequency is, more or less. And we can improve significantly the bit rate by moving from VHF to S-band. The problem with that is a satellite transmits a little more than a cell phone or order of a cell phone, and it's about 700 kilometers away. The orbit is 500, but it can go from 1,000 to 500 depending on the if it's on the horizon or just above. And if you ever wandered outside of the countryside, like you saw, you can't really get a cell phone reception, 1,000 kilometers away. And the reason is that you need specialized antennas to do that. You need the antenna to be aiming towards the cell tower or the receiving end. And that makes the satellite more complicated. So it cannot be just a simple antenna that shoots radio waves everywhere. You need to focus the energy towards the ground station on the Earth in order to be able to transmit in this S-band. So it's kind of the trade here is between just you want to have more data rate versus just you need to make a more complicated satellite that can point the antenna towards the ground station as it flies around. That makes things a little more complicated for those CubeSats because of the limited energy available, but it is possible. It's done before. It's only a matter of how important it is for this use case.
One important thing to note here is that this system is scalable. Essentially, that's kind of the limitations of a single satellite, but it's possible to kind of linearly scale all those rates of the number of requests you can serve by just putting more satellites in orbit, and that will just scale linearly. So instead of kind of having one, say for this specific certificate transparency system, instead of having one accumulator, you'll have multiple, and then you'll essentially check your certificates against the corresponding partition. The other thing is there's been some exploration of what's called the logs of logs. So essentially, instead of kind of having, say, taking specifically the example of using a Merkle tree as an accumulator, instead of having kind of one Merkle tree, you have sort of a Merkle tree that aggregates the roots of many other Merkle trees. So there essentially would be something that aggregates a bunch of certificates, or it can be other types of data for other applications. And then it would transmit the roots of those aggregates. And thinking about that, it actually suggests how you apply to blockchain applications or things like cryptocurrencies and transactions, financial transactions. So essentially, it's a ledger, and it's a ledger with a limited bandwidth. But what you can do is essentially you can aggregate large blocks of many, many transactions, and then you can report them to the satellite that records them, and that becomes the ledger that attests to a certain history of transactions that took place. Yeah, so I'll talk a bit about the aftermath of that, and mention an actual blockchain design that's happening on top of those Cube satellites, and that's been taking place in NYU. In terms of the software, we examined various cryptographic libraries. I won't go much into that because we're close to time, but essentially it's possible to use pretty standard state-of-the-art cryptographic libraries that are widely used in crypto applications. So that essentially can guarantee that you're using standard, well-tested cryptography with timing protections and timing channel protections and so on. Kind of don't need to re-implement something of your own. Some more applications that we mentioned back then in the paper is things like trusted public parameters generator for crypto schemes, a trusted party for different cryptographic protocols. Trusted timestamping is an interesting one because nowadays in different smart contracts we see the need for delayed execution, or we see cryptographic constructions for VDFs that can be potentially a simple kind, very conceptually simple alternative to that. And then also a replacement of proof of work type of mining for cryptocurrency. So essentially a transaction verification system that's not based on a proof of work because you have those trusted parties. And that's something that actually a group in NYU, after seeing this paper, started designing, and at some point they reached back to us to kind of discuss the different constraints around what a satellite can provide in this regard. So with that, we'll take some more questions if there are any. And yeah, thank you very much for checking out this talk.
I was curious about how much Kapton you would have to use to shift the moment of inertia, and also I assume that because you're deploying antenna afterwards, you have to take it off like right before you load it in. Is that the case, or can you load it with like some amount of Kapton in there, then like check the moment of inertia while it's in orbit to verify?
That's an interesting question. So I mean, you don't wrap the satellite on the outside, right? Because you have solar panels, that's going to be detrimental to their ability to do that. So you do this just before you assemble the solar panels at the outside of that. They have a very simple interface of just wires. And so it doesn't interfere with your deployment mechanism. And you can measure the moment of inertia after the satellite is deployed. Regarding mass, so because the mass of the satellite is so low, it's 1 kilogram, movements of tens of grams is sufficient in order to create a noticeable change in the moment of inertia. So you can either do this by, taping some weights randomly inside the Kapton while you wrap it in, or you can just increase the density as you go. These are just a few options. There are also others looking at random processes of glass and the way it forms. And if you open it, it breaks and then shatters, and then you cannot reconstruct it in the head. But it's an interesting construction because it's a physical entity, and it's very challenging to imitate that.
Thanks.
Again, thank you to Yonatan and Jan, both great guys I've gotten to know a little bit over the past couple of months. Really glad that you were able to present this work. Great to have you. Those of you watching on YouTube, thanks so much for joining us. If you want to be informed of any of our future talks, research funding opportunities, quarterly newsletters, all that kind of thing, you can go to research.protocol.ai, scroll down to the bottom, and drop your email in our footer to sign up for that list. We'll also put some links about PL research. If Jan and Yonatan want, we'll link to some of the work that they've been discussing here in the description, which you should be able to see below. And that's it. Thanks for joining, everyone, and we'll catch you next time.